In today's video, we're going to take a look at section 9.3, which is equations quadratic in form. And this is going to combine the techniques from 9.1 and 9.2 to allow us to solve more intricate problems, some word problems, and some problems that look a little bit more sophisticated than what we've seen before. And the first problem you have there is a word problem. It's one of our shared work problems again, but this one will have a little bit more difficult twist. I've just kind of summarized the facts of this problem here, where we have two people. They're going to take 4 hours if they work together at a job, and alone one of them could do it in one less hour. So just like before when we had these problems, we're going to start by making a little table here. And we have worker 1, person 1, and we have person 2. And we're going to make our 3 columns here. They each will have a rate. They'll have amount of time that they've been working. And if we multiply those, then we will get the amount of job that they do. So about those rates, well, their rates are different. One of the workers does work faster than the other because it says here that one of them could do it in one less hour. So if person 1, his rate is 1 over x, because he could finish the job in x hours, then person 2, his rate is 1 over x minus 1. He would take 1 less hour. He's the person working faster. The amount of time they've been working at it, well, it says right here that they're taking 4 hours to do this, so the amount of time in this problem is 4 hours. And keep in mind the fraction amount of job that gets done is rate times time, just like distance equals rate times time. So here we have, for person 1, 4 over x, and for person 2, we have 4 over x minus 1. And I don't have a lot of space here, so I hope you get the idea here. It's pretty much the same setup as we had before. So we take the fraction of job that's been done for person 1, we add it to the fraction of the job done by person 2, and they will finish one job. So these look like problems that we've had before, and keep in mind what we do with problems like this is back from chapter 7 now, is we want to multiply through by the least common denominator. And the LCD here is x times x minus 1. If we do that here, we will end up with 4 times x minus 1 plus 4 times x equals x times x minus 1. Now I'm kind of out of space here in my slide, but here's what I'd like you to do is you're going to take this, rearrange it, you will get a quadratic. And that quadratic you're going to solve, and think about how to solve that one. At this point, you really do want to pause this video and think about how to solve that. It is going to be one that I would suggest you're going to use quadratic formula for. So you might want to pause this and finish it up, and I'll give you some space here. If you do use the quadratic formula for this one, you should find that there are 2 solutions, that x comes out as about 8.5. I guess that's in hours. This problem is in hours. Or x equals 0.5. But you do have to check these. This means 8.5 would mean that person 1 would complete the job in 8.5 hours, and the second person would finish the job in 7.5 hours. And that's reasonable. If we look at the second solution, however, the second solution would say that, let me find a new color here, person 1 would complete the job in half an hour, but if I try to plug it in here now, this means the second person would complete the job in negative 1/2 hour, and that clearly can't happen. So there's only one solution here. So we're back to our distance rate time problems again. Okay, we'll only do a couple more of those. All right, the next 3 examples are all algebraic in nature. Take a look at this one. I think our first inclination here might be to multiply this all out. For example, to multiply that, combine some like terms, distribute this, and make it all one nice polynomial. But I'm going to suggest a different method that's going to serve you down the road. We're going to use a little substitution here. What I mean by that is both terms have 4x minus 3 in them. So I'm going to make a new variable. Let's say y. I'm going to let y equal 4x minus 3. If I do that, I can rewrite this as y's. I have 2y squared plus 7y plus 5 equals 0. Quite nice. And I hope and pray that this factors. Unfortunately, I've given you one that does factor. 2y plus 5 plus 1. You can verify that that does work out. So we'll have y equals negative 5/2 or y equals negative 1. But keep in mind this problem is about x's, so I now need to go backwards again and think about this substitution I did. No, I guess that green doesn't show up real nice, does it? Let's get a new green with this one. A little bit better. Okay, y equals 4x minus 3. Well, I can now substitute that back in. It means 4x minus 3 equals negative 5/2, or 4x minus 3 equals negative 1. And I can solve both of these now. This one over here on the right side looks like it's a little bit easier to do. I can add 3 to both sides, so 4x equals 2. I get x equals 1/2. On this side, I'm going to add 3 to both sides. I get 4x equals, let's see, I get 6 halves minus 5 halves. I actually got 1 half equals 1 half. And I can divide it by 4, x equals 1/8. I don't have a lot of room on the screen. So 2 solutions here, and there they are. Okay, which is the same answer you would have gotten if you had multiplied that all out. All right, second problem. And the last 2 problems here, and even the one before, I'm really going to try to push this substitution method on you because it makes some of these problems a lot easier to look at. I have an x to the 4th here, and I really don't do much with x to the 4th problems ever. So I am going to use substitution here. I'm going to let y equal x squared. And you think about what happens there, that means that I end up with y squared minus 13y plus 36 equals 0. Well, fortunately, this problem factors. Starting off with some easy ones here to factor. Y minus 9, y minus 4 equals 0. That means y equals 9 or y equals 4. And now I can go ahead and back and substitute back in what I used here. I can go back and substitute this back in. Y equals x squared equals 9, or y equals x squared equals 4. And I'll use my square root rule here that I can square root both sides here. X equals plus or minus 3. Or x equals plus or minus 2. Substitution method comes in very nicely. Now the first 2 problems you did have alternate methods of doing, but think about this last one. This looks pretty nasty. Well, this one I'm kind of forced to use the substitution rule. So after the last 2, hopefully you see how the substitution rule works. I have something here raised to the 2/3 power, and something here raised to the 1/3 power. So think about the substitution I'd want to do here. I'm going to let y equal the cube root of x to the 1/3. And think about why I'd want to do that, because if I have this here, this means y squared now. So I have 2y squared. I have 11, well, x to the 1/3 power is y, plus 12 equals 0. Okay, and you want to take a minute and see if this one factors. I believe this one does. I think I've given you some that all factor here. 2y. Got y. Let's think about this a little bit. I got minus 4, I got minus 3. That's kind of nice. Y equals 3 halves, or y equals 4. But now I have to go back in and re-substitute what I did before. Get my yellow marker here. There we go. I have to go back and substitute this in. So I have x to the 1/3 power equals 3 halves, or x to the 1/3 power equals 4. Well, what would I have to do to these to get x back? Keep in mind, the 1/3 power is just a cube root. So I'm going to cube them both. So x equals 27/8, x equals 64. 2 solutions. Okay, so the substitution method comes in very nicely. Okay, that's it for this section, and you have some review problems there to do.